Entire screen. Okay, so Hadi, is it? Are you getting my screen?
Yes, sir. Yes,
Okay,
sir. It's visible.
okay, thank you. So as you know that this is on uh, Monte Carlo integration. So Monte Carlo name, if you search, it is a casino in France. Okay, where the gamblers use it to play a lot of games. And if you read the history of probability theory, you will be amazed at that a lot of work has been done by gamblers. They use it to apply a lot of probability theory concepts while gambling, so that they could guess what is the probability of winning and what is the probability that next card will be this. So there is one such a casino or such a place in France that is called Monte Carlo. So it has been, since this technique is based on probability concepts, so it has been named in honor of those people. So let me just begin with this slide. Just look at the integral. Okay, there is one typo, log of 1 plus. I have written 1 equal to, it is 1 plus. But just imagine, do you think that you can evaluate this integral? No way, right? It's not possible to have a closed form expression. And I don't know that some of you might have done a course on numerical techniques. You might have studied Simpson's rule, trapezoidal rule for approximating such integrals. But let me tell you that when it comes to such complicated three-dimensional integrals, trapezoidal and Simpson's rule, they are very slow for this. Okay, they will take a lot of time, lot of resources. So this is just one of the motivations for studying a alternative technique which can simulate such integrals. That's called Monte Carlo simulation. And since we need probability theory concepts, so I will be revising briefly, not in detail, a little bit of probability theory. Then I will be I will be sort of revising or just giving a statement of a theorem called law of large numbers, which is actually at the back of Monte Carlo integration. Then I will introduce Monte Carlo integration and important sampling and conclude. And all these things will be backed up with live Matlab simulations also. I am using Octave, which is an open source, and I encourage using open source. I strongly discourage, if any one of you have pirated Matlab, it is a crime. So you should stop using pirated softwares, from today. Rather, you use student version, or if you have a license, which is very difficult, it's very costly. So otherwise, go for Octave. All the Matlab code runs in Octave equivalently, and it is free of the cost, license free. You don't need to pay for it, and it is fully legal. Okay. Now, it happens in various scenarios, and it started with physics, but now we can see in various engineering applications. In fact, a couple of days back, one of the electrical engineering research scholar, he has been my student also in research methodology. So he just sent me a message on WhatsApp that in his research problem, it is related to electrical engineering problem, I need Monte Carlo simulation. So I told him that, do you know that we have a session on it? He said, I don't know. So now I don't know whether he is here. Just I am telling this because its application is almost in every branch of engineering, not only in communication, not only in physics, but also in electrical engineering, even civil engineering, mechanical engineering, and even finance. Okay. So one of the issues in Monte Carlo is to evaluate non-evaluative definite integrals, that is, which are not possible to get the closed form expressions. We know some rules, but they don't work for higher dimensions. Now, before I will demonstrate what Monte Carlo means, is, see, I could have directly shown you the code, but that doesn't work, right? You should understand what is happening actually. So that's why I have a revision of sort of probability theory. So all of you might have done a course. I guess most of you. See, there may be some PhD scholars, they definitely have done. MTech scholars definitely have done. Now, if we have those BTech students who have crossed their fifth semester. They are now going towards sixth semester. I think they also might have done a course on probability and statistics. Now, in probability theory, the fundamental thing is the probability space triplet. That is, we have a sample space. I will be giving an example on coin tossing. Suppose you have a coin tossing experiment, so it's only possible to have head or tail. So all such possible outcomes, we call that sample space. Then we can have all the subsets of this sample space. Suppose if you take coin tossing, it can be an event of head, event that it is a tail, or it can be a compound event such that we say it is either head or tail, or even it can be an event which says that it is nothing, null set. So you toss a coin and nothing happens, although you know that some of these are very sure, they are certain to happen. Suppose if I ask that I toss a coin, what is the probability that it will be either head or tail? You will say 100%. It will be either of the two if it is a normal coin. Similarly, if I say that I toss a coin and nothing happens, neither head or tail, it stands alone in between, you will say it is not possible, it is impossible event. And if I say what is the probability that it is head, or what is the probability it is tail alone, then you will be a little bit puzzled and you will say, okay, 50-50 chances. Now, to get idea of that, what is the likelihood, we have a number called a probability, which is associated with each and every element of event space, which we call this f. So that is having some properties. It should be non-negative, definitely. uh, you know it cannot be negative, and it should be additive. Okay, if I am saying what is the probability that it is head or tail, that is what it means by A union B, then it should be probability of head plus probability of tail, given that A and B are disjoint, that is, they have nothing in common. And probability of whole sample space, again, that means that it is either head or tail, is 1. It's obviously probability that something happens is 1, right? See, we can ask a question like, what is the probability it rains? It will have some chance. Maybe tomorrow, since it is rainy season, so there are higher chances of raining, 70%. What is the probability it will not rain? Maybe 30%. So if you take overall, what is the probability that there will be some weather tomorrow? You will say 100%. Something will be there, either rain or no rain. So that is what it means, that probability of omega is 1. Now, we don't like to play with sets, we'd like to play with numbers. So that is why we introduce random variable, which is a function from sample space, all the points from in sample space, to the real numbers. Suppose in this case, we have this head. Okay, we map this head to suppose 0, and we map this tail. If tail occurs in coin tossing, we map it to 1. Okay, now this, here we have now numbers. Okay, so we call this as x, and this is what we call random variable. Now, if a random variable is discrete valued, okay, discrete valued means, if you take a die example, so there can be possibilities 1, 2, up to 6, right? So this is your actually sample space, and there can be a lot of events. It's not only that what is the probability you get 1 or 2 or 3. You can even ask what is the probability you get odd number, even number, prime number, right? Multiple of 2, multiple of 3. You can ask such questions. And since in die experiment we directly get numbers, so we don't need any mapping, or we can say it is a one-to-one mapping. We directly have these numbers as random variable. This set is called random variable. Okay, it is actually random variable is a function, that is important. Now, how to characterize a random variable? We can ask this question: what is the probability that a random variable capital X? So whenever I write a capital X, it means it is a random variable. That is, we don't know what value will it take. But when I write small x, it is a notation. Small x means that after the experiment has taken place, this is the value it has taken. Okay, it's called small x. So what is the probability that a random variable takes some particular value? Suppose in case of coin tossing, this small x can be either 0 or it can be 1. Okay, so I'm asking what is the probability x is equal to 0 or x is equal to 1. So that I denote by small p subscript random variable x times the particular value small x. This is called a probability mass function. You can also ask that what is the probability that a random variable takes value up to small x. Okay, so if you take die experiment, there it becomes more prevalent. Suppose you throw a die and you ask that what is the probability the number you get at the top of die is less than or equal to 3, right? This is a valid question. You can also ask what is the probability that the number you get is less than or equal to 4, less than or equal to 5. So if you go on asking about this question about all the possible values, so you will get cumulative distribution function corresponding to this random variable CDF, and notation is it is denoted by capital F. Okay, CDF we will most of the books denoted by capital F. Then for continuous random variable, we cannot ask, I don't have time right now to demonstrate that. For a continuous random variable, it is not at all value giving any information to ask what is the probability x equal to x. Okay, for continuous it will be always 0. Okay, so I don't have right now time, then it will take long time to demonstrate that. But you can always ask what is, even for continuous random variable, that is a random variable which takes values on continuous real line, what is the probability that a continuous random variable takes some value x less than or equal to x. Suppose there is a random variable x which takes values on 0 to suppose 1. It takes any value between 0 to 1. So I can ask what is the probability x less than or equal to 0.5. No one can stop me in asking that. It is a valid question. You can ask what is the probability that x is equal to 0.2, 0.3, 0.4, 0.01, whatever. So then if we differentiate this cumulative distribution function, we get something called density function, probability density function. Okay, it also what is the significance of probability density function? So at any particular point small x, it tells you the likelihood of that value, whether if the value is less. So if you plot any PDF, suppose like this, it means that wherever there is a peak, it means these values are highly likely, and near the tails the values are very less likely. Okay, if you have any quick question, you can write in chat right now, because if there will be any confusion, then you will not get what I want to say. If you have any question right now, let me check the it's here. Yeah, so no questions I am seeing in chat. Yeah, because I would like session to be interactive. Okay, yeah, so no questions. I will move ahead to next slide. Now, here are some of the common distributions. One of the distribution which we will be actually using also in Matlab simulations right now is uniform distribution. So uniform distribution means that suppose you take any two numbers a and b, such that a is less than b, then for any value between x between a and b, the density function has constant value 1 by b. So it's like something like this. Suppose this is a, this is b. Okay, so let me go back here. If you look at the condition, I told you that that the probability p should satisfy that probability of omega of whole sample space should be 1. Okay, so in terms of density function, it means that the integral over this probability density function should be 1. That actually means area under the curve of this density function should be 1. So if you take a density function which is constant, uniform, that is why uniform, that is the likelihood of any values of x between a and b is same, then what should be the height so that area is 1? So it should be 1 over b minus a. Okay, because this length is b minus a, so for the area should be 1, height should be 1 by b minus a. So that is why uniform density function is equal to 1 over b minus a for x between a and b. Suppose if a is 0 and b is 1, we have a notation for it. We say that x is distributed as uniform UNIF 0 1. It means x is a random variable which takes values between 0 and 1 with all equal likelihood, equal density function. Okay, so in that case fx of x is simply 1 if x is between 0 and 1, and it is 0 otherwise. Okay, then we have a very other famous density function called Gaussian density function or distribution. So it is something like this. Okay, it has why this distribution is important, that has a separate reasoning. We will not go into that right now. And also one more example is exponential distribution, which looks like something like this. Okay, these are different density functions. Since we are going to approximate integrals, and integrals are related to continuous random variables, so in Monte Carlo simulation we will not be dealing with discrete random variables. Now is an important result from probability theory. Now I think this most of you might not have seen, okay, because it is not taught in the usual courses here. Maybe some of the PhD scholar or MTech scholar may have seen in some course or personally, but as long as BTech curriculum is concerned, you might not have seen this. Now, what is it? Suppose you have n random variables. As an example, you are having, suppose you are tossing a coin. So every time you toss a coin, you toss coin first time, you represent the outcome with x1. You toss coin second time, you represent the outcome with x2, with x3, x4. See, there are two people. One is the person who is performing the experiment, and the other person is just guessing. He is not performing the experiment. Okay. So when you are tossing a coin, the person who has a coin, the other person may guess about what is it. Is it head or tail? So he denotes the first outcome with capital X1, second outcome with capital X2, third outcome with capital X3, and capital X4, so on and so forth. Okay. Since they are all identical, because they result from the same coin tossing experiment, they are identical. Okay. So you can generically represent in general with some random variable x. See, the person who does the experiment, who sees the value, for him the x1, x2, x3 values are known. And the person who doesn't see these values, for him x1, x2, x3, xn are random variables. They are sequence of random variables. Okay. Now, what can you at most do? If you know the density function or distribution of the random variable, you can compute, suppose, mean in this way. This is the definition of mean. Integral the value a random variable takes and the probability density function of that random variable dx. Limits will be defined according to the problem. In general, we can write minus infinity to infinity, but it depends upon, suppose if you have uniform distribution, if you go back here, you have a uniform distribution between 0 and 1. So expected value of such a random variable will be between 0 and 1. Integral between 0, 1. X fx of x dx, right? Then you can put on the value of density function, you will get the expected value. So this is called true mean, also expected mean, theoretical mean. Okay, because you are not knowing the exact values, but you are knowing just the density function. But the one who has performed the experiment, he knows the values of xi's. He can compute something called sample mean. Sum over all the values he got 1 by n. Simple. Statistical sample mean. And we denote it by mn. Okay. So for a newcomer, this little bit becomes difficult. But mn is actually a random variable. Because it is known only by the one who is doing the experiment. But for me, suppose I don't know the outcomes of the experiment, I am just guessing. So for me, mn is a random variable. It is a sum of random variable, hence random variable. Okay. Now, what is the law of large numbers? Law of large numbers says that this mn, as n goes to infinity, so like we write in limits, limit n goes to infinity, mn, it will converge to the true mean, expected value. Let me little bit dwell more here because it is very important. So I will just show you one example. Suppose you take a coin tossing experiment. Okay, so all of you know that if it is a fair coin, then if I ask you what is the probability of head or probability of tail, all of you will say it is 0.5. Okay, we have 50-50 chances of having a head or tail. But what is its experimental proof? So experimental proof will be something like this. You will toss coin, suppose 10 times, then you may toss 50 times, then you may toss 100 times, then you toss 200 times, 500 times, 1000 times. What you expect actually is that half of the times you should get head, half of the time you should get tail. But what will you observe? Suppose if you do it only 10 times, you will not get 5 heads and 5 tails. Very rare. You may get sometimes 8 heads, 2 tails, or 3 heads, 7 tails, so on and so forth. But you observe as the number of trials increase, you will get almost 50-50. So if I plot like this, if this point is 0.5, this is actually what I want. Now if and this is n, the number of trials. So 10, 50, 100, 200, 500, 1000. So what will you observe that at 10 you are not having so this is on the y-axis I am plotting fraction of times head takes place, that is number of times we get head divided by n. Okay, suppose if you get 7 heads and 3 tails, so this fraction will be 7 by 10, which is 0.7, so something here. Then 50, when you toss coin 50 times, suppose you get 40 times head and you get 50, so you get 30 times suppose head and 20 times tail. So fraction of head is 3 by 5. Okay, so 3 by 5 will remain somewhere here. Similarly at 100, what you will observe is that as n increases, you are getting values closer and closer to 0.5. So this is one of the demonstration of law of large numbers, that as n increases, your sample mean, it converges towards the true mean. Now the next statement is little bit more advanced, not meant for definitely BTech people. That what does it mean actually? It means that uh, probability that difference between the sample mean and true mean exceeds by a small amount epsilon. It is bounded by variance of this random variable x divided by n times epsilon. Okay, so those who know the little bit of analysis and advanced probability, they can see that as n goes to infinity, this term goes to 0, and hence this probability will converge to 0. So it means that the sample mean cannot exceed even by a small amount from the true mean as number of samples goes to infinity. Now, for all of you, you take a general message, even if you don't get most of the things I said in this slide, just take a message that if sample mean, no, I have this slide, if sample mean mn, if I increase number of samples, suppose you take first 100, then 1000, 2000, 3000, as you increase number of samples, this sample mean will be closer and closer to the value of mean you get by using theoretical distribution function. Okay, it will be more clear when we will do the some Matlab coding also. Now I will now move one step ahead. Suppose you have some function g of x. Now you have a random variable x, you can define function of random variable x, g of x. As an example, g of x can be suppose x square. Okay, it means whatever value random variable takes, you are just squaring that. In some cases, suppose g of x can be sine of x. Whatever value random variable takes, take a sinusoidal function of that, and that is g of x. Okay, if you want to find the mean of not random variable but expectation of function of random variable. Okay, so here is I think one typo. It should be g of x. I will correct it while sharing this presentation with you. So expected value of g of x will be, so if you go back, if you see this expected value of x, it is x times fx of x, right? Now if instead of x it is expected value of function of random variable x, so what should you do? Replace this x with g of x and then the density function. Okay, now what will law of large numbers tell us about this? Now we have again samples of random variables. We are generating samples x1, x2, x3. They are all generated with distribution fx of x. Okay, as an example, suppose if I choose distribution as uniform distribution between 0 1, it means all of these x1, x2, xn, they are random variables which take values between 0 and 1, all with equal probabilities. And we can define corresponding function or every sample g of x1, g of x2, g of x3, so on and so forth. Then the sample mean of such functions will be summation g of xi 1 by n. Very simple. And law of large number tells me that as this n increases, this sample mean will converge towards the true or theoretical mean or expectation of g of capital X. In other words, I can write for finite n, okay, this sample mean is approximately equal to expected value. Okay, now let me now take a particular example. This will be easy to understand. Now what I am going to demonstrate is called Monte Carlo integration, and it is a uniform sampling basis. See what it means. I generate random variables x1 up to xn. Okay, they are generated, or we say they are drawn from a density function which is uniformly distributed between a and b. It means all of these x1, x2, xn, they are random variables, and they can take value between a and b with a uniform probability distribution. That is, they have equally likely probability of taking any value between a and b. Then law of large numbers states that what is the expected value of g of x? Okay, so just recall, or let me write it here. So this actually is integral of g of x fx of x, right? This is definition of expectation of function. Now what is fx of x? Go back to this slide where I have defined the distributions. So for uniform distribution, we just now learned that fx of x is 1 over b minus a whenever x is between a and b. Okay, so that is why I have written here 1 over b minus a. Since it is a constant, it will come out the integral. The limits will be now a to b and g of x. Now what does law of large number says? This is approximately equal to sample mean, that is 1 by n, summation of I is equal to 1 to n g of xi. Now if I bring this b minus a, multiply it here, what I get is this thing, that integral from a to b g of x dx is approximated by b minus a by n summation g of xi. Now this g of x, it can be any complicated integral, it can be something like this. Okay, in any coding language, Matlab, or you can use even C language, any language, you can define a function and you can evaluate this function value at any point, and then just you have to take the average, and you will get the approximate value of this integral. Now here is a small algorithm based on this. This will be called the Monte Carlo algorithm. What you have to do is, first thing, you have to generate n random samples from uniform distribution AB, store that in X, compute g of X, and then this will be computed as a mean of g of X times b minus a. Okay, so enough talking. I think let me go to the So here is this Octave. It looks much uh, you know similar to Matlab. So I will be writing it here on the command line. So in Monte Carlo simulation, first of all, you have to decide how many samples you want to take. Suppose I will take 500 samples. Okay, I defined n equal to 500. Now I need to generate, if you know go to this algorithm, so we need to generate n random samples which are uniformly distributed between a and b. So for sake of simplicity, I take a is equal to 0, b is equal to 1. So I need to generate uniform random variables which take values between 0 1. So in MATLAB you have a function called rand. Rand, if you type and just press enter, you will always get values between 0 and 1. Okay, so rand is a function in MATLAB which generates uniformly distributed random variables. Okay, every time you get a value, but you will never get value outside 0 1. You will always get between 0 1. Now if I want to generate 10 such random variables, I will write 10 comma 1. If you want to generate a matrix of 10 cross 10 of such random variables, you will get a matrix of where each entry is uniformly distributed. It's a random matrix. Now in my case, I want to get here, I got these n. This is now x1, x2, x3, x4, up to x. I will store this in x actually. Okay, yeah. So if you look into this x, okay, so look into this x. So these are, you check the values of x, they will be, all of them will be between 0 and 1. Okay, so you can think of them as x1 to x 500. Okay, see here, they are the entries of this 5. There are 500 samples, all of them uniformly distributed. Okay, nice. Now what is the next step in algorithm? You need to compute g of x. Now let me first decide that which integral I want to evaluate. So let me take some simple integral so that we are able to verify it also. Let me take g of x as e to the power minus x, and let's suppose we need to integrate 0 to 1 e to the power minus x dx. Since it is a very simple integral, we are doing it for just comparison. So let me see what is this value. So it will be, if you evaluate this integral, e to the power minus x between 0 to 1. So I can say it is 1 minus e to the power minus 1, right? And what is the value of 1 minus e to the power minus 1? We also know that we can, so it is 0.63212. Just note it down. 0.63212 is the exact value up to 4 decimals. Okay, because e is irrational. So this is the exact value of integral. Now what? Now let's do Monte Carlo method and see that we get what we want. Now what is the next step in Monte Carlo? So we have generated, suppose I took n 500 and I have generated 500 samples of uniformly distributed random variable. Now I want to compute the function over this. Okay, so what I need for that is I need to define. I hope that you have now enough training of MATLAB, so you must be good in defining the functions. So I can define, suppose my function is equal to, this is one of the ways, and then exp minus x. Sorry. Yeah, just a moment. my function is this is at x exp minus x. Now it is okay. So I have defined a function my func. So if I write my function, suppose 0, it will evaluate the function at 0, at 1, or any other value, whatever. Okay, so now I need to compute the value of this function e to the power minus x for each of these random samples. So I will write my func then x. Now what it has done is it has computed the value of the function at every random sample I have generated. Okay, in other words, if you look at this, so xi here are the entries of this rand function which I have already run. Then g is your e to the power minus x, and when I write my func of x, I am actually computing the value of this function at every random sample. Okay, let me store it in y. Now what is then the integral equal to? B minus a times mean of g of x, but b is 1 and a is 0 here. Okay, so b minus a is just 1, I don't need to write. So integral will be simply, if I write it, b minus a times mean of this y, because in y I am storing this g of x values. Now what is the value we got? 0.6295 and 0.6295. Okay, approximately close. Now let's just do one thing. Let's do everything and let's increase n to 1000. I have previously n was 500. Now let's take it to 1000 and repeat everything. X is equal to rand n1. Nice. Then my function is already defined. Okay, e to the power minus x. Then y is equal to my function evaluated at all the random samples. I will just make it like this. Then I is equal to, now I have got 0.63711. 0.63711. You see, this is closer to 0.63212 than 0.6095. Now one more demonstration will be, let us take n equal to 50. Let's take it very less. We will see that there will be a lot of inaccuracies. So here is this x. I have generated n random samples. N is 50 now. I will compute the function e to the power minus x at every random sample, and then see, it is 0.59786. 0.59786. This is n is equal to 50. So we are seeing that this is n is equal to 500. This is n is equal to, sorry, this is exact value, n is equal to 500 and n is equal to 1000. So we see that for small n we get less accuracy, but as n increases the accuracy improves. I have shown it for simple function. You can define any complicated function you wish. Suppose if I write my function is equal to, let's write here sine of x also. Okay, so there is a reason I have taken this function. Although this also you can evaluate using integration by parts, but it is a little bit complicated than previous function. Now let me take this y is equal to, okay, and I will take now, suppose 500 is pretty good. So x is equal to rand and this, then y is equal to my function. Now my function is e to the power minus x times sine x. Okay, oh sorry, you had to put here a dot. So here is one point in Matlab. Previously if you see, I defined function in this way, e to the power minus x star sine x. This is valid if x is a scalar. Since here x is a vector, it is an array, right? So we cannot put star directly because we had to do element by element multiplication. So you might have studied in Matlab. For that you need to put star. Even in function difference you need to put star. Now it will compute the values. Okay, now y contains the value of e to the power minus x sin x, where x is the values of all the 500 random samples. And now I is equal to this thing. So this is the value of integral. So we have computed this integral. Okay. Yes. So I have taken this example purposely because with this example I will demonstrate something called important sampling also. Now I would like to, because interrupt here all of you. I have got some questions. Mm, uh, One is, can we do this simulation on any MATLAB software or on any MATLAB software? You can do in Python, you can do in C, you can do in C++, Julia. That is a new language. You can do in R, whatever. It is a general algorithm. Okay, both are similar and commands the same, one open source and the paid. There is some syntax difference. Yes, there is a minor syntax difference. Okay, that is not a huge. There are some functions in MATLAB which are not available in Octave, but you can always define such functions. Oh, and also there is a plotting difference. Now, do you have any conceptual question right now regarding what we have done till now? Any doubt? Because it's not fruitful just to go on speaking. If you have any question, you can write in chat. And whatever I have done till now, so RAND function and that is 100% same MATLAB as well as in Octave. No difference at all. What I have shown you today is exactly same thing you can write in MATLAB as well as in Octave. Okay, so there is, I haven't used any advanced package, anything. Okay, although there may be some ready-made packages for Monte Carlo simulation also, but not fruitful to do. Okay, so no questions are coming there. Let me continue. Now, important sampling. Uh, I don't have time right now to demonstrate the variance, okay, of this, but I will just give some brief hint what actually variance means. Now, this will be understood by those who have good understanding of probability theory. See, look at this particular thing. Okay, it is the approximate value of expected value of g of x. In other words, it is the approximate value of the integral. If you look at now, let's take a look at this. Your integral is now approximately equal to b minus a and summation of g of xi. This is a random variable. That is what I want to say. See, x1, x2, they are all random variables, sequence of random variables. They are drawn from the same distribution, okay, but they are all random variables. It's like you toss a coin 100 times, you know the value, but for your friend, it is like 100 random variables. Okay, he has now 100 random variables. He doesn't know whether you got head or tail at every try. Then function of random variable is also a random variable. So if x is random variable, so is x square, x cube, sine of x, they are all random variables. Okay, so g of xi is random variable, summation g of xi is random variable. So if I denote this quantity as, suppose, I, so this I is a random variable, right? So for a random variable, what can you define? You can define mean, you can define variance, right? So we can define variance of this I. Let me go to the whiteboard. So I is b minus a by n Okay, so I can define mean mu I, which is the mean. So expected value of I, just a moment, what happened to this? Sorry. So expected value of I, that will be expected value of b minus a by n summation g of xi. Okay, so b minus a by n is constant, summation is here, and expected value of g of xi. Now this expected value you can compute because you are given the distribution of xi, fx of x. Similarly, you can compute variance of I. What is definition of variance? Expected value of I minus mu I square, right? And it is also equal to expected value of I square minus mu I square. Those of you who know these formulas, then you can compute this expected value of I square and so on and so forth. Now, variance is related to the error actually. Okay, variance is related to the error. How much variation is there in the values, right? And you will see that this variance, it depends on n. Okay, as n increases, variance will decrease. Okay, so that is how we compute the variance of these Monte Carlo integrals. Now, it has been seen that if your function which you want to integrate, suppose you take this function, you wanted to integrate it using Monte Carlo simulation. What you did is you generated x1 to xn from uniform distribution, right? 0 1. Suppose you wanted this integral between 0 and 1, and then you computed the value of this function g of x at all of these x1 x2, and you got g of xi. Okay, I is equal to 1 to n, and 1 by n, b minus a is 1. So this is what you got as an value of integral I. Now, there is a particular result in Monte Carlo theory which says that if you closely observe the function, now listen this very cautiously, and you find that some part of the function looks like some probability distribution. Now, can those of you who got this point, can they write in chat, in this function e to the power minus x sin x, do you see any part of this function as any well-known distribution? If yes, you write in the chat. And there are some questions, I will take that, but first you write in chat, do you find in e to the power minus x times sin x, there is any part in this function which looks like some distribution which you know already? If yes, you write in chat. Khande Sajid, no, it is not bell shaped. Okay, to save the time, let me go to this slide. Now you look at this slide, and then there are only 3 distributions. Out of this, which distribution you see is a part of this function? Come on, it's very simple. It is exponential. Yes, so first reply I got from Amir Sharfuddin. Yes, okay. So it is exponential distribution. This one, e to the power minus x, looks like exponential distribution. Now look at this very carefully. So I have integral of e to the power minus x sin x dx between 0 to 1. Okay. Now you forget the limits for time being. Just look at this. If I define sin x as some h of x, right? And if I define e to the power minus x as some fx of x, correct? So you can write this as fx of x, h of x, d of x. Now I want to see a probability genius in among you. What is this integral of h of x, fx of x, dx? What is this in terms of probability theory? Yes, this is some famous quantity you know. Just a hint. Now fx of x is exactly exponential distribution, right? See, if you see exponential distribution in general, it is 1 over mu e to the power minus x by mu. If you put mu equal to 1, you will get fx of x is e to the power minus 1. It is an exponential distribution with mean 1. Okay. No, it is not convolution. It is expected value of h of x, nothing else. And it is expectation with respect to exponential distribution. See, what is expected by h of x? It will be integral h of x times the density function, right? Now in current case our density function is e to the power minus x and h of x is sin x, right? So it is integral e to the power minus x sin x dx. Limits are between 0 to 1. Is that clear? Okay. Then what it says that it is not necessary always that you will generate samples using uniform distribution. No. Just look at the function carefully. If you can find some well-known probability distribution type of thing within the function, take that as probability. Now what will you do? See, what will we do? We will now generate x1, x2, xn. We will not generate them using uniform distribution but exponential distribution with mean 1. Then I will compute h of x, I will take as sine of x. Okay. And I will compute this quantity I is equal to 1 to n h of x I 1 over n. Now this sample mean, because samples are generated from exponential distribution, this sample mean will be converging to the expected value of h of x. But now expected value of h of x is e to the power minus x sin x dx. Is this clear to all of you? Okay. So this type of sampling, where you are not sampling from uniform distribution but you are sampling from another distribution depending upon the shape of function, that is called importance sampling. Okay. And it has a rigorous proof that importance sampling can result in reduction in variance. Okay. So here is how we do it in general. Suppose you have a integral g of x from a to b. Okay. And you find some distribution in it, let that be fx of x. You divide this by fx of x, multiply by fx of x, right? Then this you take as suppose h of x. Okay. So this is simply expected value of h of x. Okay. And this will be approximately equal to 1 over n summation h of x. That is very simple. So now your importance sampling algorithm will little bit change. You have to generate x now from not uniform distribution, any distribution. Okay. Suppose in this example e to the power of minus x sin x, this distribution was exponential. It can be. Now I will ask a question. Suppose I want to integrate e to the power minus x square cos of x. This integral is not evaluative. Suppose again limits I take between 0 to 1, whatever. So now can you tell me which type of distribution you see in this? E to the power minus x square. Yes, Gaussian, right? Muhammad Salik. So now what will you do? Okay, it is not exact Gaussian. There is something missing. What is missing? There should be 1 over under root of 2 pi e to the power minus x square. But what you can always do is, suppose you have e to the power minus x square cos x, right? So you can write 1 over 2 pi and you can multiply here root 2 pi, right? Then this becomes your fx of x, and this is your h of x, right? So you can write this as expected value of h of x. Now what you need to do is you need to generate x1 to x2 using Gaussian random variables. I will now demonstrate it in Octave. Let me first take some questions were written there, so then I will miss it. Sir, is my func as g of x? Yes, it is g of x. Okay. The theorem you stated, is it valid for experimental results as well? That is with higher n. Is the convergence? Yes, it is. See, Muhammad Saleh, it is probably converged. Okay, that will take maybe 1 hour or so if we show the proof of convergence. It has a rigorous proof, so it is probably converged. So experimental values definitely will follow it. There is no doubt in that. Okay. Can we say Monte Carlo is converting continuous distribution into discrete? No, it is not converting continuous distribution into discrete. That is something different. Definitely, we see practically whenever we do something, we are taking discrete values of from a continuous distribution. That is we can say, but that doesn't mean you are converting continuous into discrete. That is a different thing. So that we do using uh, so that we study in, if you study some good course on machine learning or pattern classification, there are non-parametric methods where we can do that. Not right now. Okay, now let us, so here is the exp R&D. I think if I am right, exp R&D is to generate exponential random variables. Let me take help to, okay, what is the syntax of that? You don't need to memorize. Okay, see, this is one issue in Octave. uh, if you have Matlab, every package comes with it, but in Octave we have to load some packages. So it is asking for statistics package. So pkg load statistics. Now I have loaded a stats package. Now I can use exp. I will first see its syntax. Now it has a syntax like this. The first parameter is the mean, that is 1. The second parameter will be what is the size. Okay, I have to write it in this way, 10 cross 1, I think so. Wait. uh Return matrix samples from the mean lambda, and we call this. Wait, this is comma. Yes. SPRD. Okay, sorry. So now to generate 10 random variables, suppose I need n is equal to 10, then we write exprnd, okay, then ones n comma 1. So what it will do is it will generate 10 random variables. They are all distributed with exponential distribution mean 1. Okay, because see this I am at this, the syntax is inside the square brackets I am mentioning the mean. Suppose if I write manually, that will become more clear. 1 2 3 6, it has generated 4 random variables. First is having mean 1, second is having mean 2, then mean 3, then mean 6. If you want all of them to have same mean, then you write ones n comma 1. It generates n length vector, all of the entries are 1. So hence it will generate 10 Gaussian this exponential random variables with mean 1. Now if I take n is equal to 500, right, and these are the 500 random variables, I will store them in x. Now my function I will modify is same, e to the power minus x sin x. Nice. So y is equal to, okay, now here is one important thing. What should be my function now? I have generated samples using exponential. My function should be now sin x only. Is this point clear to all of you? Because I have now generated, it was my function was e to the power minus x sin x when I was generating using uniform distribution. Now I am generating from exponential. So the important sampling says that you have to take now the mean of the second part of function sin x. So my function is now sin x. Okay, and so I will write now y is equal to my function of this. Okay, and now I is simply mean of y. So this is 0.48. If you remember previously also we got 0.48 value as of the integral. Okay, so now what small experiments you can do at your place is you can do it both using usual uniform sampling Monte Carlo and importance sampling, and with the number of samples increased, you will see that the error with importance sampling decreases. Okay, as another example, suppose if you want to now do this example, e to the power minus x square sin x dx. Okay, so now what I will do is I will write it as 1 over under root 2 pi e to the power minus x square, but I need to multiply it over with e to the power root 2 pi sin x. Okay, now this part I will call as fx of x. This part root 2 times sine I will call it as h of x. Okay, dx integral. So what should I now do? I will now need to generate x1 x2 distributed from fx of x, which is now a Gaussian distribution. Of course, mean 0, variance 1. Now in Matlab as well as Octave, you have RANDN. Okay, so this generates Gaussian random variable, and you see Gaussian random variable can take any value between minus infinity to infinity. Okay, so but most probable values are near this mean, that is near 0, but it sometimes can take very large values also. Okay, now again if I write array and d, sorry, 10 comma 1, it will give me 10 Gaussian random variables. Now I have n is equal to suppose 500, then I have x is equal to randn. Okay, rand means uniform random variable, randn means normal, that is Gaussian random variable. By default it generates mean 0, variance 1 random variables. Okay, I need to generate n cross 1, so that is n is here 500 different samples, right? Now my function will remain same, that is a power of importance sampling. The function remains very simple. Just see, look at the simplicity. Why importance sampling will help? If you used uniform samples, your g of x was e to the power minus x square sine x. Computing e to the power minus x square sine x every time is not simple, right? There is a exponential square operation involved. But now when you generated Gaussian random samples, then you have to compute simple sine x function over that, which is relatively computationally simple. So that is the thing of importance sampling. So now you don't need to evaluate e to the power minus x square. You need to evaluate sine x over all these samples. Now your y is my function of this, and you just find the mean of this y. This will be the approximate value of integral 0.010891, right? So you can, if any one of you know Simpson's rules or trapezoidal rule, you people can at your places, you can compare it with those values. Okay, so let me just see the conclusions. So conventional numerical integration, if you have studied at all, which like as I told, Simpson's rule, trapezoidal rule, they are not suitable for high. Okay, sorry, I need to show you one case of higher dimensions also. Just one, double integral, how to. So may I know from Hadi how much time we have? Hadi?
Sir, actually, you have about 50 minutes now, sir.
Okay, yeah, I will take that minute only. Let me show you a very simple
Sir, 50 minutes.
50 50.
Yeah, 50.
Okay,
So you
then.
can take it as long. Yes.
Yeah, actually I was not well, so I don't have too much to show you. I just prepared it in very haste. So let me just show you one example. Suppose I have this integral e to the power minus of, suppose, x square plus y square dx dy, right? And double integral, suppose between 0 to infinity. Okay, now it is a double integral. Now how will we proceed for this? I would like to write this in editor rather than because there will be a lot of things. Now look at it carefully. First of all, we will define our function, my function. Now, so I think this way you might have already done the how to define inline function. So this is called inline function. I will write here x. Say I will write x1 or x or y. Maybe that is okay. Then what is there? It is exp minus x square minus y square. Okay, but since x and y are arrays, we have to take care of this. So we have to write here dot. That is very important, right? Because if it is a scalar, then it was okay, but you need to now raise it to power 2 element wise. So you need to write, you have to take care of these things. Sometimes even a very efficient research scholar is stuck because of these small mistakes while coding his problem. Okay, so take care of these things. You are dealing with array or you are dealing with scalar, then accordingly you have to use dot. So this is definition of function. Now let me take samples as 1000. Now I will initialize a vector x with zeros. This is the way to initialize. It will have n elements, okay, n cross 1 vector. Now see, now I need to generate two random variables here. One x, the other y. Okay, so first of all I will run a loop for I is equal to 1 to n. Then I will generate, suppose x r, I will call it x random as RAND. So I am using a very simple uniform sampling here, and YR as RAND. So now what is it doing? It is generating two, because I have now two variables. So I am generating two separate sequences of random samples. X1, X2, X3, so on, Y1, Y2, Y3, so on. I store them in XR and YR. And then in every element of vector X, I will store the value of my function computed at XR and YR. Okay, is this clear? Here is one minor difference between Matlab and Octave here. In Matlab, you have to write for and end. In Octave, we write and for. Okay, not a big deal. Now, I will now, the value of integral will be simply now mean of this x. Okay, let's run it. I will not run it in that way. I will just, what happened to this, evaluate, run selection. So it may take some time because now we are running a loop here up to 1000. Meanwhile, till the time it runs, or as it shown, yeah. So this is one integral. So you can now we can make it more complicated, and suppose I write here cos of 2x plus 3y dx dy. Now can anyone tell me that what will be the, using importance sampling, if we use now importance sampling for this integral, which distribution you see? Any part of this function it looks like some distribution? Yes, it is Gaussian. It is two-dimensional Gaussian distribution, right? Yeah. So you can, it is now here is the thing. It will be 1 over 2 pi. It is no more 1 over root 2 pi. I will tell you why. See, if you have one random variable, suppose fx of x, it is 1 over root 2 pi e to the power minus x square by 2. Now if it is another random variable y, it is 1 over root 2 pi e to the power minus y square by 2. Now if x and y are independent, then the joint distribution of fx and fy, they can be written as the product of the two. So which is 1 over root 2 pi e to the power minus x square by 2 times 1 over root 2 pi e to the power minus y square by 2, which is 1 over 2 pi e to the power minus x square plus y square by 2. You have to take care of this. It is not 1 over root 2 pi for joint distribution of Gaussian random variables. That is important. So now if you want to compute this thing, I will write here by divide by 2 purposely, so that it It is cos of 2x plus 3y. Now what will you do is you will generate r a n d n. You will now use this. So xr is r a n d n, yr is r a n d n, and your my function will be cos of 2x plus 3y. We can even demonstrate it there. Okay, someone has written, yeah. So here is the value of this integral. This was our e to the power minus x square plus y square. Okay, even that integral can be evaluated very easily using important sampling also. But now let us do this one. So what are the changes we need to make here? Let's see. First of all, my function will have to change. It will be now cos of 2x plus 3y. Okay, and very simple, I have to write here r a n d n, r a n d n. That is it. Things got simplified. And let me take only 500 samples so that I can quickly run this code. And here is, yeah. Okay, now you see this important sampling, how important it is. Again, it simplified our operation. We don't need to evaluate the sample values using this function e to the power minus x square plus y square and so on and so forth, rather than only cos of 2x plus 3y, because we could identify one part which is looks like some. Now you can go for 3 dimensions also. Yes, very simple. You need to use one more variable, zr, r a and d. Simple. So here is the value of integral. Now I will take you back to that imagined slide, this one. Now do you all of you are comfortable with, can all of you compute this? Forget important sampling initially. You can here nothing looks like any distribution. So now I want to, from comment section, can all of you compute this integral using Monte Carlo? Look at this monster. Yes, initially you would have, oh, how can we do it? Now I think very simple. Just need to find my func, right? In Matlab, generate x, y, z. You need to have 3 random variables, x, z, x, y, and y, z, and use r and d function, and you can compute it. Even this complicated integral. In physics and quantum mechanics, some examples are there where you even have 6, 7, 10 dimensional integrals also you have to evaluate. At that time all the numerical technique fails. Your Simpson rule fails, your trapezoidal rule fails. So Monte Carlo is the only way. In fact, Monte Carlo was initially used by physicists only. Okay, they were the first people who used it, and now it has very huge application. Very recently, something called MCMC, Monte Carlo Markov chain, has found very tremendous application in machine learning also. So it is a huge topic. Books have been written on it, lot of books. It's not as simple as it appears. The proofs are very much involved, and like important sampling, there has been lot of new techniques have been proposed. You people can explore that. uh, you know this much I have in this short lecture. I think you have some more time. If you want to ask more questions, you can ask right now.
If anybody has any questions, they may unmute themselves and ask it.
Yeah, you can even ask on audio also.